Welcome back to the Explainer. If you're tuning in, I know you're the kind of focused learner who absolutely loves getting into the actual nitty-gritty of how things work under the hood. So today, we're unpacking a really fascinating topic: battery management system communications, or more specifically, we're zooming in on the unsung hero of high-voltage engineering, the BQ79600Q1 communication bridge. We'll be using the manufacturer's own application notes and system data sheets to completely break down how this single, totally unassuming little component prevents catastrophic failures in modern electric vehicles. Right off the bat, we run into the million-dollar engineering question, don't we? How exactly does a standard, super delicate 5-volt microcomputer safely talk to a massive, potentially lethal 400-volt battery pack? Because you really have two major engineering villains to conquer here. First, there's the intense electromagnetic noise from the vehicle's inverter and motors that can completely scramble your critical data. And second, you've got this massive high voltage that can, frankly, vaporize your logic boards in a fraction of a millisecond if there's a short. Well, the bridge chip we're examining today is our absolute shield against both of these destructive forces. Here's our roadmap for the journey. Number 1, BMS architecture and overview. 2, power supply design essentials. 3, bridging the communication gap. 4, crossing the isolation barrier. 5, the daisy chain network. And finally, 6, conquering noise and interference. Let's dive in. Starting off with Section 1, BMS architecture and overview. Okay, take a close look at this master layout. On the right, you've got your battery management unit, MCU. Think of that as the brains of the entire operation. Now, sweeping over to the far left and the bottom, you'll find the actual battery cells themselves, along with the heavy-duty, high-voltage contactors. But right in the middle, that's our ultimate gatekeeper, the analog front ends and digital isolators. This is the great divide, guys. The communication bridge literally straddles the line between the safe, low-voltage logic domain, where the computer lives, and the high-voltage measurement domain, where the immense power of the battery pack resides. Actually, before any physical communication even tries to jump that divide, the software boot-up sequence acts as a strict zero-tolerance safety gate. It's this rigorous 3-step protocol. First, step 0 is the hardware wake. The power rails go valid, but the hardware safing paths absolutely hold all contactor energy off. None of it gets through. Then, step 1 initializes the CPU without changing a single actuator output. And finally, step 2 locks in the system's safe defaults. This whole dance guarantees that physical readiness translates into strict software safety long before a single byte of data is allowed anywhere near that battery. Moving on to Section 2, power supply design essentials. So powering this chip isn't as simple as just slapping it onto a battery. It has to carefully balance multiple internal voltage domains all at once. The BAT pin handles the internal wake-up mechanisms. CVDD supplies 5 volts specifically for the vertical communication interface. DVD actively regulates 1.8 volts for the internal digital logic circuits, and VIO closely matches the host microcontroller's input-output voltage. But you really need to pay attention to that third column, the decoupling and bypass capacitors. Placing these tiny little 0.1 and 0.22 microfarad capacitors as close to the pins as physically possible is simply non-negotiable. It's crazy to think about, but missing a component the size of a grain of rice will allow internal voltage ripples to crash the entire chip, completely blinding the vehicle's computer to the battery state. All right, Section 3, bridging the communication gap. So how do they talk? The bridge chip actually supports 2 main languages to communicate with the host microcontroller, SPI and UART. Now, SPI uses 4 wires: MOSI, MISO, a clock line, and chip select. It's great because it offers significantly faster data rates. But there is a super vital, easily overlooked design quirk hidden deep in the application notes. The MISO pin on this specific chip is pulled high when it's idle. Because of that, the SPI interface literally cannot be shared with other slave devices on the same bus. It dictates exclusive control over those microchip pins. UART, on the other hand, is way simpler. It just uses a dedicated transmit and receive line with no external clock required at all. And honestly, you can really see the impact of that choice when you look at the physical board layout. On the left, the UART interface is incredibly clean. It ties up just a couple of GPIO pins on your MCU and requires very minimal trace routing. But look at the right. The SPI interface demands more traces, more pull-up and pull-down resistors, and eats up way more pins. So as an engineer, you're directly trading the physical routing simplicity of UART for the higher bandwidth of SPI. It's a real make-or-break architectural decision that you have to lock in right at the start of your design phase. Which brings us to Section 4, crossing the isolation barrier. I like to think of this isolation barrier as a protective moat around a vital castle. The host microcontroller is our safe castle, and the high-voltage battery pack is the dangerous wilderness outside. To get data across without letting lethal high voltage sneak back in and fry the logic board, we use transformer isolation. These 1-to-1 ratio transformers provide galvanic isolation. That means there's absolutely zero physical electrical connection between the left and right sides. No copper wire connects them. Instead, the AC-coupled data signals transfer across invisibly via magnetic fields. It's literally a magnetic fortress wall, letting the safe data pass out to the battery while keeping high-voltage, common-mode noise from rushing back in. Section 5. The daisy chain network. Let's trace the signal out to the battery pack itself. Notice the COM-HP and COMP-HN pins on the right side of the chip block. These are your crucial differential lines. They carry the data out to the first cell monitor unit in the stack, usually over heavily shielded twisted pair cables. And that twisting, that naturally cancels out a massive amount of external electromagnetic interference. We call it a daisy chain because the communication signal literally hops from the bridge up to monitor number 1, gets processed, and then hops to monitor number 2, traveling sequentially up the entire high-voltage battery pack to read the temp and voltage of every single cell. But check out the brilliant safety mechanism built into this chain ring architecture. Because communication here is entirely bidirectional, the host can choose to send messages north up the stack or south down the stack. Why does that matter? Well, imagine a wire snaps from heavy vehicle vibration or a connector fails mid-pack. The system instantly detects the fault and just reverses its communication direction to reach those stranded devices from the other side. It ensures no cell ever goes unmonitored, which is absolutely crucial for preventing fire risks. Plus, it supports reverse wake-up. The main host computer can actually go to sleep to save the 12-volt battery while the car is parked for months. Meanwhile, the ultra-low-power bridge chip keeps a vigilant watch, only waking the main system if a critical battery fault pops up. Pretty clever, right? Finally, Section 6, conquering noise and interference. You see, an electric vehicle's inverter is incredibly noisy. It's constantly throwing out these massive, high-frequency voltage spikes everywhere as it drives the motors. So engineers have to fight two very specific types of noise. First is differential mode noise. That's the noise that goes out one wire and returns on another. We suppress this using X capacitors, placing them tightly between the communication lines to absorb those spikes. But then you have common mode noise. This stuff is sneaky. It goes out on both wires simultaneously and tries to find a return path to the chassis through invisible, stray capacitance in the surrounding air and materials. To fight this stealthy interference, we bring in the Y capacitors. Just look at exactly where those X and Y capacitors physically sit between the noisy inverter on the right and the isolated chassis. The X capacitor bridges the lines directly, killing the differential noise right at the source. Meanwhile, the Y capacitors give that sneaky common mode noise a highly attractive, incredibly low-resistance, safe path straight into the chassis ground. It essentially traps the interference instantly, bleeding it off before it can ride your delicate communication lines back into your sensitive microchips and scramble all your data. But here's the thing. Relying on capacitors alone just isn't enough. The ultimate weapon against signal degradation is how you actually draw the physical circuit board. The manufacturer's datasheet lays down this strict, totally non-negotiable law for routing the daisy chain. It says, keep differential traces as short as possible and as straight as possible. Keep the differential traces on the same layers. If you loop your traces, if you make sharp angles, or if you jump between layers with vias, you instantly introduce impedance mismatches. You're basically creating microscopic antennas that will eagerly suck up all that inverter noise and completely crash your communications. So think about the journey we just took. We traced a communication signal from a simple software wait command inside a safe 5-volt computer, pushed it through precise voltage regulators, sent it across a magnetic moat, routed it up a bidirectional twisted pair daisy chain, and forced it through a brutal gauntlet of high-frequency electromagnetic noise. Rigorous design, meticulous reading of the application notes, and a very deep respect for the physics of high voltage, that is literally the only thing standing between a perfectly functioning electric vehicle and a catastrophic system failure. The next time you glance at a datasheet, just remember that every single capacitor placement and trace routing rule is there to prevent a disaster. So the question is, are your circuits ready? Thanks so much for joining me on this explainer, and as always, keep learning.